In this example, we have a circular disk that is rotating about a beam, and then we have a fixed axis rotation as a result of that. Now, the coordinate frame axes are already assigned for us. There is our x-axis, there is the y-axis, and then there's the z-axis. And the formation of these axes are due to the right-hand rule. So the right-hand rule will apply for this question. If it is actually not told otherwise, you need to assume that the right-hand rule is used in general. This is a general consensus all over. Anyways, so we have this right-hand rule to be applied here. And at a certain instant, the magnitude of the velocity of A, so what we are talking about, the velocity vector's magnitude, is measured to be 3 meters per second. Okay. Then, at the same time, it is measured that this magnitude is decreasing at a rate of 7.2 meters per second square. Now, as soon as you see this meters per second square, you need to understand that this is an acceleration. But is it the total acceleration magnitude? So acceleration of A point's magnitude? No, it's not. Because what we are talking about here is about the magnitude of the velocity. We are saying that the magnitude of the velocity is decreasing. Remember that in the acceleration vector, we have two parts, depending on which coordinate frame you use. You have the part about an and at, right? Now, the tangential component of the acceleration, at, is due to the change in the magnitude of velocity. An is due to the change in the direction of the velocity vector. So what we are talking about here as 7.2 is actually at vector's magnitude. So this is 7.2 meters per second square. And remember, when we are using these motion equations that we have talked about in kinematics, in regards to the acceleration, the tangential component of the acceleration, we use r alpha to be equal to a tangential part. Okay, so, or we can just show it as a vector and its magnitude if you want to do it like this. So this is told to us as 7.2. So the other part of the acceleration is going to be calculated as r omega squared, and that would be the magnitude of the an vector, the normal component of the acceleration. And that's something we don't know yet. What we know is that this r alpha is 7.2 meters per second squared. The good news is that we know the information about r. R is 200 millimeters. That means 0.2 meters. So we can find the alpha angular acceleration by dividing 7.2 by 0.2. And we receive this information of the angular acceleration, 36 radians per second squared, but then it is decreasing, so it should be in the opposite direction with respect to the z-axis. Now, how do you understand that? Place your thumb in the z direction, and then you will see that this omega, there's the pointer by the way, this is the arrow, this omega is defined in the positive sense with respect to our right-hand rule. So alpha in that sense should be in the opposite direction, should be in this direction. And therefore, when we are going to represent this angular acceleration as a vector format, we need to use this negative sign saying that it is in the negative direction about this k vector, negative 36 radians per second square. And this alpha is true, this angular acceleration is true for any point on this circular disk. This point will experience the same type of alpha, this point will experience the same type of alpha, and what is asked in the question is that we need to identify this alpha first, this is what we have done, and then the total acceleration of point P, total acceleration of this point. The alpha that it's going to experience is the same alpha, nothing different. And when we are talking about total acceleration of point P, we are saying that this acceleration that is composed of the normal and tangential directions in point P. So we need to calculate both of these. And this is how we calculate that, right? Our alpha would be to calculate the tangential component, and our omega squared, it will be required to calculate normal direction. We can also rewrite these in terms of the vector format. The vector format would be alpha cross product r vector would give us the information about tangential component of the acceleration, and omega cross product in the parentheses omega cross product r would provide us the information about the normal component of the acceleration, and this is a vector. Okay. So we have already determined alpha, good for us. We can calculate a tangential acceleration vector, but we don't know yet omega. This is something also we can calculate from the given information, because we already know that the velocity, magnitude of the velocity of point A is 3 meters per second. And we can calculate the velocity as omega r as the velocity, right? So since we know the r for A point is 0.2 meters, velocity is given to us as 3 meters per second. We can find the omega as 15 radians per second. And if we are to define it in a vector format, the direction of it, as it is given as a positive velocity, will be a positive 15 k, k defining the direction of this angular velocity vector. Then, as we have all this information, now we can plug in that information, substitute that information in these equations. This part is the tangential part of the acceleration, at vector. This part is the normal part. This is the an vector. And all you need to do is run these equations. But in order to run these equations, you need to also define RB vector. RB vector can be defined in a number of ways, but this is a vector at the end. You can use any coordinate frame. But since we are using the coordinate frame assigned here as XYZ coordinate frame, we can as well define the location of RB by using this coordinate frame, and that will have a component only in the y-axis from this rotation center. The location of B will be only in the y-axis by 0.15, and the direction is the J direction. Now, if we had a point around here, let's say point C, and then the magnitude will be 0.1, let's say, meters, then RC would be defined, RC vector would be defined from the rotation center, let's call it O, to be 0.1 J, again in the y-axis it will be. However, this time it will get a negative sign because it's in the negative direction. Also, you can find different locations here. Let's call this point D, and then the D point will probably, oops, let me just try to rewrite that, RD. D point will probably have a combined location as negative, let's say 0.1 I and a negative 0. I'm just making up the numerical values, by the way, 0.1 J. The negative sign is to be there because it's in the negative direction of x and y axes. Negative signs are true, but then the 0.1 magnitude is just something I made up just to make you see it. And if you want to calculate the acceleration of B point, then you're going to use this information. As you can see, it is used already at these locations. If you're going to calculate the acceleration of C point, then you're going to make use of this vector. If you're going to measure or calculate the acceleration of D point at that instant, you're going to make use of this vector for the RB vector instead of the RB vector in this equation.